Okay, so we're going to look a little bit more at hypothesis tests. So we've already talked in a previous session about terminology, and then we started trying to calculate these critical values. And we've seen snippets of answering a full hypothesis question, but in this session we're going to try and do a bit more of the whole process. So that is the full step process of defining terms, finding critical values, and writing the result of your hypothesis test. It is largely an exercise in just demonstrating knowledge rather than calculation. The exception to that being, as we saw in the previous session, the calculation of the critical value. That's generally the only part in which you'll be doing calculation. But hopefully this session will give you another opportunity, another chance to make sure that the knowledge we've been building up all comes together and wraps itself in sort of one neat package of being able to perform a hypothesis test. So to start off with, I've got 3 scenarios here, and you don't need to know about hypothesis testing to answer this. It's more about your intuition, and I think perhaps it might be quite obvious for some of us. Depends on how you think of defining the answer. So in the first case, and I looked this up, in London apparently 40% only of people pass their practical driving test the first time. So then the question is, out of 80 first timers, how many do you expect to pass? Approximately 3.5% of people in the world can speak French. If I was somehow able to randomly pick 200 humans completely unbiasedly from the earth, how many of those 200 humans do you expect to speak French? And if I flip a coin 50 times, going back to coins, how many times do you expect it to land on heads? So for each of those 3, I'm just looking for a number, and see if you can tell me what that number would be. I'll let you pause. Okay, so hopefully we've come to the correct conclusion here, which is we're just going to multiply the percentage by the amount of things, right? If I can put it that generally. So literally, what is 40% of 80? Divide by, divide by 10 times 4. I expect 32 people to pass. 3.5% of people in the world can speak French. Again, I'm going to do 3.5%. or 0.035 times 200, which would give me, in this case, well, that's just 3.5 times 2, so 7. 7 of those humans will speak French. Sorry, let me rephrase that. Not they will. I can't know for sure, right? I could pick 200 people, get unlucky, none of them speak French. Or I could get really lucky, maybe 20, 30 of them speak French. The key thing is I'm talking about the most likely outcome out of all the possible individual outcomes. And then finally, flip a coin 50 times. How many times do you expect, and again this is a very key word, the expectation, how many times do you expect it to land on heads? 50 times the probability, which is a half, 25. Okay, now all of that might seem obvious. Just multiply the amount by the probability, that's the expected value. But this is actually something quite specific to certain kinds of distribution. What you'll notice, or what you may not have noticed, but what you'll notice now, is that for all 3 of these scenarios, they can be described by a binomial distribution. That is, I'm doing a number of trials. Each trial has a certain probability of happening, and I'm counting how many times it happened. Right. So for instance, with the humans, I'm doing 200 trials of picking a human. Each time I pick one, there's a 3.5% chance that human's going to speak French, right? Or person. I don't know why I keep saying humans. So there's a 3.5% chance that a randomly chosen person will speak French. So we multiply the number of trials n by the probability p. And this is the principle I just want to clarify on the next slide. So this principle is that the expected value, and this is actually a mathematical term, it's not just English, it's a mathematical term, of a binomial distribution is NP. Right, that's the expected value. And for our purposes, we can think of it as the most likely outcome. And N, of course, we just want to clarify, is the number of trials, and P is the probability of a single trial being successful. So it's useful to be aware of this, because when we're about to go forward into hypothesis testing, it's good to keep in mind that you have some idea of what a typical value should look like. And typical value, that's not a mathematical term. Expected value is the mathematical term, but we kind of use them to mean the same thing. So typically, you should be expecting about n times p for your x value. Now, that's not to say that it's the most likely thing to happen overall. Let me clarify that. What I mean is, with 50 coin flips, 25 is the most likely outcome out of all 51 possibilities. However, it's far more likely that it doesn't hit 25 than it does, right? So all the individual 51 outcomes from 0 to 50 have a probability. All of those are quite tiny, a lot of them, but the one that has the biggest number is 25, the probability that I get 25 heads. But just because it's the biggest doesn't mean it's a majority. It's still going to be it's still going to be far less than a half, right? So it's not actually the most likely in terms of will it happen or will it not, but it is the most likely individual outcome. Okay, so that I just wanted to get out of the way and make completely clear. So be really aware of this concept of the expected value, namely the number of trials times the probability p, n times p. So now let's move on. That NP stuff will possibly come up later. What I've done here is I've tried to lay out a sort of series of steps for doing a hypothesis test. If you look online or in a textbook or wherever, you may get a slight variation in how many steps there are. It may not be 7, it might be 5 or 6 or 8. Perhaps some of these steps are combined into one, but generally speaking, it's the same process. And really, what you should think of this on screen here is the step-by-step process by which you're answering an exam question. Because frankly, within the topic of hypothesis testing, the majority of your practice should be in the form of exam practice, and that's mainly because the questions, and I've said this before, they don't actually vary that much. Not as much as, say, other topics in mathematics can vary. There is some problem solving stuff, but generally speaking, if you're given a hypothesis testing, you're most of the time going to be following this set of steps or something similar. So it's just a case of learning the process. So the process is as follows, and it's written here generally, but then we're going to try and put it into practice. The first thing you do when you get the hypothesis test question, for the most common type of question, is you're going to define the test statistic in words. It may be in the question already, but you're going to pull it out and say, this is the test statistic, right? You describe it in words. For instance, the test statistic is the number of heads I get when I flip a coin 50 times. Okay. In fact, let's go with that example for now. Let's say the coin flip 50 times. We'll use that throughout. So that's the test statistic. It's the number of heads I get when I flip the coin 50 times for that scenario. Number 2, define the population parameter in words. The population parameter, that's your P, remember. In fact, let me just put here in brackets. Population parameter we usually call P. And again, you want to say in words, what is it? So in the coin example, it's the probability of landing on heads. So step 2 is not telling the value. It's not p equals p less than p greater than. It's just what is p? What does it actually represent? That's why it's in words. Okay. Then for 3, we're going to define the test statistic with a mathematical model. So we've defined it in words, and in this case we said it's the number of heads I get. As a mathematical model, you want to write, in this case it is binomial that we're going to be working with, so I'll just say it is binomial here, and you'll want to specify your n and potentially your p. Okay, p maybe, if p is your population parameter, which it usually is, then it may just be the letter p. You won't have a number, and n you will usually have a number. Okay, but whatever information you're given, its x is modeled as some binomial. Okay, and that's defining it precisely. Okay, next, define the null H0 and H1 hypotheses, or hypothesis, if it's just one of them. So you're going to write H0 colon P and then something, H1 colon P and then something. Okay, and that something, we've seen already how that works. It'll either be a not equal, for H1, it'll either be a not equal, a greater than, or a less than. For the H0, it's always going to be, so we might as well write it in, it's always going to be equal to something, right? So in our flipping coins case, by default P is a half, and for H1 it's whatever you want it to be. Do you think it's more likely, less likely, or do you think it's just completely biased? So it'll be P greater than a half, P less than a half, or P not equal to a half, depending on what your alternative hypothesis is. Okay, and that you will usually get from the question, depending on how it's phrased. So that's step 4. Then step 5, calculate the probability of getting the observed value, or worse, of the test statistic. This is the one where you actually do some calculation. So this is number 5. This is basically the previous lesson, right, is what we were talking about there. So I guess I won't go into too much detail right now. We'll look at the example soon. But that is effectively what we're doing in the previous lesson, is to get the this probability of getting the observed value of the test statistic. So that will become clearer when we look at the examples. And then 6 is you're going to compare the probability that we just got in step 5 to the significance level. So is it less than or greater than? Okay, so is it less or greater? And you're going to use, when I say using one tail, what I mean is with 1 you're going to just use S, and with 2 tail you're going to use S over 2. And then finally in 7 you're going to write a conclusion in, write a conclusion, oh that was supposed to be a space, in words, okay, in which you either say the H0 is accepted, or the H0 is, and my face is covering it there, rejected. Okay, so broadly speaking, that's the process, but it's best understood by doing it in practice, I think. So let's have a go at doing that. Actually, just one more thing before we look at the example. I used this phrasing or worse in the previous slide, but I just want to sort of clarify what that means a little bit. If you remember binomials, they tend to have this sort of hump shape. The hump itself can sometimes be a bit wonky, it might not be symmetrical. Perhaps to draw it a bit more generally, you know, maybe it looks a bit something like this, right? But there is generally a sort of peak, in a binomial. And do we remember that was the most likely outcome, and we just talked about what that is. That's effectively at Pn, right? So Pn or NP, I think I'll write NP, I'm more used to writing it that way. That is your expected outcome, right? It's the thing that's most likely to happen. At least, sorry, it's the outcome out of all possible outcomes which is most likely to happen. So that gives you kind of a ground for what counts as really high and what counts as really low. So let's stick with the example of the 50 coin flips. If I say I flipped a coin 50 times and I got 40 heads, does that seem very high or very low? In this case, what you're actually doing, perhaps without realizing, is you are thinking, well, the expected value is 25. 40 is more than 25, therefore high. But in perhaps a different scenario, let's say it wasn't a coin, which is more obvious. Let's say I do something 100 times and let's say the probability of each success is 0.2. So I do something 100 times. Each time I do it, there's a 20% chance of it succeeding. How many successes will I get out of 100? If I said I got 40 out of 100, does that seem very high or very low? Hopefully you can see it's very high, and it's because, again, you're thinking, I hope you're thinking that 100 times 0.2 is 20. So I would expect 20, but you got 40. That's high. So this concept of what's very high or what's very low for an outcome, for a test statistic, for an observed value of a test statistic, this concept is very relative. It's relative to what you actually expect. And what you actually expect is something around NP. So when I say or worse, what that means is, for instance, if I said to you, this is my binomial, and let's say I actually got 30. Or worse, in that case, means, well, on the diagram here, that's 20 is the expected, 30 is over here. So the or worse would be 30 or more, right? So this part here is the probability that x is greater than or equal to 30. But or worse doesn't always mean that number or bigger. It can also mean that number or smaller. And it will mean that number or smaller when the observed value is less than your NP. So in this case, NP is 20. So let's say I got, I don't know, 15, right? So I did this process, I did 100 times, and it happened to be a success 15 out of 100 times. In that case, 15 or worse for this scenario means the probability of getting 15 or less. So you always go more to the extreme. Okay, it's still a little bit general what I'm saying here, but what I'm just trying to point out is that this concept of getting a certain value or worse basically means that value or the other values that are even more unlikely. And that can be either bigger or smaller depending on which side of the NP that your observed value is. Okay, so hopefully that makes sense. You can see it for this example, this specific binomial. Hopefully if I gave you any number now, you would be able to identify what the or worse area is. Is it the stuff that's above or below? Okay, so as a quick test, let's just do one more. Let's say I do this binomial, and let's say I actually observed, let's see, 35. Is my or worse above or below the 35? So in this case, my NP is equal to 32. I observe 35. So 35 is higher. It's higher than expected, right? So that means my or worse What I mean by saying that value or worse is what's the probability of getting 35 or more, because it's higher. Okay. Cool. All right. Now let's look at the example. So the standard treatment for a particular disease has a 2/5 probability of success. So on a single trial, there's a 2/5 chance of success. A certain doctor has undertaken research in this area and has produced a new drug which has been successful with 11 out of 20 patients. Okay, I'm going to start writing some numbers down. So n equals 20, p, which is our population parameter, is 2/5, and the test statistic is modelled by 20/2/5. Okay. The doctor claims that the new drug represents an improvement on the standard treatment. Okay. By the way, the 11, that's our observed value. Okay, that's the observed value of the test statistic. So it's 11. The doctor claims that the new drug represents an improvement on the standard treatment. So our null, well, our null is that p is 2/5. That's by default. Our alternative is that p is in this case greater than 2/5. And we're going to now test at the significance level of 5%, the claim by the doctor. Okay. I'm just going to replace all these 2/5 actually with 0.4. I think in this context it's probably a bit better to have them as decimals. Okay, so that there is just all the information I've just thrown on a page in a sort of random order. Let's follow our actual steps. So I've got the 7 steps in front of me that we looked at the previous slide. So I will number them, but just keep in mind that in an exam, don't number them because the numbers won't mean anything. It's only according to the specific way I've given it to you. But my number 1 was define the test statistic in words. So that is X represents the number of patients successfully treated with the drug. Okay, out of 20 patients. Okay. Number 2, define the population parameter in words. P equals, well, let's do colon because it's not really an equation. So P represents probability of the drug successfully treating a patient. When you do hypothesis testing, you are going to have to put words on the paper. You can't get away with just throwing a few numbers and a few symbols. You do need to write words. Represents probably the drug successfully treating the patient. Okay. Number 3, define the test statistic with a mathematical model. X is modelled by the binomial 20, and now I'm going to put here P. Right. The reason I'm not putting 0.4, even though I did here, but I was just making notes. I'm not putting 0.4 because we don't actually know what the value is. The whole point is that in the hypothesis test, we're going to be testing it out. So we just put P, and the hypothesis test is trying to figure out, is it 0.4 or is it perhaps something bigger? But the 20 doesn't change. No matter what, we can see it's already been done. 20 patients were asked. Okay. Number 4, let's define the null hypothesis and alternative hypothesis. The null hypothesis, well, we've got it all here actually. So that was our part 4. Okay, H1 colon is P greater than 0.4. Okay, number 5, calculate the probability of getting the observed value or worse of the test statistic. So what's the probability of getting that observed value or worse? Now we got 11. Does that seem very high or very low? So this is why we need the NP stuff. In this case, NP, where N is 20 and P is 0.4, we're assuming the null hypothesis here. If the null hypothesis was true, the default position, then I would expect 20 times 0.4, which is 8. So 11 is higher than 8. So we got higher than expected. So we want to know what is the probability of it being that high or even worse or even more unlikely. So number 5 is work out the probability that x is greater than or equal to 11. Okay, and the reason it's greater than or equal to is because we compared 11 to NP and found 11 was greater than 8. Okay, and now we're going to have to work out what that is. So the probability that x is greater than or equal to 11 is the same as 1 minus the probability that x is less than or equal to 10. And we can do that on the calculator. I'm actually just going to use the textbook. So we've got 1 minus 0.8725, and you end up with 0.1275, or as a percentage, 12.75%. And we should write it as a percentage because, number 6, we're going to compare that probability to the significance level. Now, we should also note, I'm going to put here on my notes, this is a one-tail test based off the fact that it's a greater than symbol in the alternate hypothesis rather than not equals. So it's one tail. So that means if it's one tail, I'm going to take S 5% rather than use S over 2, which is for two tail. So I'm going to compare 12.75% to 5%. Question 6 is literally which number is bigger. Okay, so let's write here 6. 12.75% is bigger than 5%. Okay, it seems obvious. You have to write it down. You have to show that you've done the comparison, not because an examiner doesn't believe that you know which one's bigger, but because they need to know, do you understand what you're doing? Do you understand which numbers you're supposed to be comparing, right? Someone who didn't understand hypothesis testing might think, oh, am I supposed to compare 11 to 5? Or am I supposed to compare 0.4 to 5? Those are all meaningless comparisons. You have to be comparing the right numbers. So that's how you demonstrate that you know what you're doing, or at least that you have managed to show that you know what you're doing. So we compare them, and then we have to write the correct conclusion. So that is part 7. Okay. So this part 7 is now words. Just have to write it up here. And let's first talk about what's happened here in this comparison. Do we take the null hypothesis or the alternate hypothesis? So I want to try and get the intuition to make sense here. We just did a test. We tested 20 patients, and 11 of them, more than expected, actually passed, got better, right? Now, the chance of that happening, or even more than 11, is 12%. So pretty unlikely, but not that unlikely, 12%, it could happen. And before we did the test, we said significance level is 5%, meaning if anything happens which is 5% or less likely, that's pretty significant, right? If you think about a significant event, it's something unlikely, right? A meteor hitting the Earth is significant. It's only happened a few times, but not that often, right? That's unlikely, it's significant. It raining in England is not significant. It happens all the time because it's quite likely. Well, that's not the reason why, but it is quite likely. So what we're saying is 12.75% significant? It's not, because we said 5% is significant, or anything less. 12.75%, although a bit unlikely, is not significant. So if it's not significant, we stick with our original thoughts, which is H0. You only change your mind if significant evidence comes along to make you change your mind. Right, so that's the intuition behind this. We stick with the status quo, the default position H0, unless something significant enough happens that makes me change my mind, and go with H1. So what are we going to write? We're going to write the test statistic oh, sorry. Let's rephrase this. I want to get the phrasing really right here. Let's just say the observation, the observed value does not show enough evidence to reject H0. Okay, so what we're saying there, and so the key words there that you want to always write in an exam is evidence and reject, or not reject. Well, there's two ways to phrase it. You can either say reject H0, or you can say not accept H1. Accept and reject are opposites, right? So you can use either one and then just stick the word not in front of it, depending on which one you're using. So you can either say reject or not accept. Or alternatively, you can say accept or not reject. Either one of those is fine, depending on which one you're going with. So there's several ways of phrasing it, but you should be using these key words. And then very importantly, you have to say something about not enough evidence. What you can't say is we definitely, or for sure, or we are convinced that we reject, that we accept H0, or that we don't reject H0. Because as in the real world, unlikely things can happen. If I flip a coin 50 times and get 50 heads, for all intents and purposes, that proves it's biased. But technically, there was a very, very small chance that could have happened by accident. So it doesn't constitute as proof, right? It's not 100% proof. Same as in a court of law. You can't 100% prove someone guilty or not guilty. You can only do it within a certain significance percentage, effectively, within reason, right? Beyond a reasonable doubt. So if you're 99% sure, it's probably good enough, but you can never be 100% sure. So that's why we need to have this phrasing in there, and that is something which is usually given a mark in an exam, or more likely a mark will be taken off you if you don't reference the fact that what we're talking about is evidence. Okay, so that's it. That's basically the recipe book to doing a hypothesis test. And as I say, what you should do is just do as many of these types of hypothesis test questions as you can, and just check the answer, and then see if what you're writing matches up with what the answer says, and try as much as possible to just line up with the mark scheme, and then you'll get an easy 6 or 7 marks in an exam if a hypothesis test question comes along. Okay, so we'll do one last one, but this time two-tail, and this time I'm just going to go straight for the numbered steps. Okay, again, you don't need the numbers, but I'm going to use them so that you know which step I'm on. So over a very long period of time, it's been found that in Enrico's restaurant, the ratio of non-veg to veg meals is 2 to 1. That is to say, 2/3 of them are of non-veg to veg meals. So a third of them are vegetarian. In Manuel's restaurant, in a random sampling of 10 people ordering meals, 1 ordered a vegetarian meal. So we observed 1 out of 10 ordering a veg meal. Using a 5% level of significance, test whether or not the proportion of people eating vegetarian meals in Manuel's restaurant is different to that in Enrico's restaurant. Okay, so the whole Manuel and Enrico thing just gives us unnecessary detail. What we're effectively saying is we're talking about one thing, which is the amount of vegetarian meals, and we just want to know if it's more or less than a certain value. So let's just be clear though, because we're going to have to write in words, so we do need to care about which person we're talking about. Whose restaurant are we testing? Test whether or not the proportion of people eating vegetarian meals in Manuel's restaurant is different to that in Enrico's. So Manuel is the person that we care about. Enrico is just giving us a value to compare against, which is a third, but we're testing Manuel's restaurant. So X, which is our test statistic, and you can see here, because we observed it, right? We observed 1 out of 10. X equals the number of vegetarian meals ordered in Enrico's restaurant. Let's capitalize the name, do it properly. Out of 10 customers. Okay, and then number 2, the population parameter P is equal to the probability a single person orders a veg meal. Okay, number 3 was define the test statistic with a mathematical model. X is a binomial 10p. Define the null and alternative hypothesis. Okay, so the null hypothesis is that the restaurants are the same. By default, we just assume everything's the same, everything's fine, right? So Manuel's is the same as Enrico. Enrico's restaurant, we had non-vegetarian to veg is 2 to 1. So that gives us P equals a third. I've just spotted, by the way, sorry, I did say it several times, but then I wrote it down wrong. We are talking about Manuel's restaurant, not Enrico's. Okay. Yeah, otherwise that's all good. And then the third comes from comparing to Enrico. So P is a third, is the null, and the alternative is, what are we testing? Test whether or not the proportion of people eating vegetarian meals in Manuel's restaurant is different. Okay, so different just means it could be more or less, right? It's not testing if it's more than Enrico's or less than Enrico's, it's just different. So it means not equals. Not equals to a third is our alternative hypothesis. Okay. Number 5. What's number 5? I said calculate the probability of getting the observed value or worse. What was the observed value? We observed that x equals 1, right? Or we observed 1. Now, what did we actually expect? 10. If the null hypothesis is true, we expect 10 times a third, which is not actually a whole number, 3.3 recurring. We'd expect about 3 people to order veg. However, only 1 did, which is lower than we expected. So to get that number or worse is therefore the probability that x is less than or equal to 1. Okay, and you could you could use your knowledge of the binomial distribution to work that out, but let's just use our calculators. The probability of x less than or equal to 1 when n is 10, and we assume the null when we do the calculation, so we assume it's a third. In this case, it should come to 0.104, which equals 10.4%. Number 6, compare the probabilities. So 10.4 is bigger than 5%. Let's change it there. So, was it significant? Well, we observed 1, and there's still a 10% chance of that happening, to get 1 or less. So, not significant enough. Right, our significance level was 5%. We didn't drop below 5. So, not significant. We're going to stick with our original assumption of H0. So we're going to say there is insufficient, and I'm going to write it a slightly different way so you can practice using the various types of terminology. There is insufficient evidence to reject H0. And then, just for good measure, write a sort of layman's, regular English-speaking person's understanding of what you're trying to say. What you're trying to say is that there is insufficient evidence that Enrico and Manuel's restaurant differ. Okay, so basically what we're saying is it seems like they're the same. It seems like they serve the same amount of vegetarian food. There's not enough evidence for me or for us to believe otherwise. Okay, so hopefully that's enough examples there. One key mistake here. If you got this far and said it, then you get the house point. Very important. I've done one thing wrong. The answer's still right, but I've made one big mistake. What did I forget to do? Hopefully you can spot it. I forgot this is two-tail, which was part of the point of doing this example. That's two-tail, which means I shouldn't have written here 5%. I should have halved that. Right? I should have halved the significance level to 2.5%. Right? Which we only do if it's a two-tail test. But it's still the same result. It's still insufficient evidence. So very much insufficient evidence in this case. Okay, so keep that in mind. That's literally the only real difference within a standard hypothesis question between those two. The difference between one-tail and two-tail is in one of them you change the significance level, in the other you don't. Okay. Okay, so there isn't that much time to try questions really, but what would be good is if we forget the second slide, just look at this first one. Please, at the very least, check what the textbook says for each of these questions and see if it agrees with what you think you would have written down. Pretty much all of these questions, it's just about writing down the right thing. You don't really have to do much calculation, except for that one step, number 6. That's the only time you do a calculation. The rest is just write it down. So for instance, number 6, look at it and tell yourself what is my test statistic, what is the population parameter. They've even given you the null and alternative hypothesis there. What am I going to calculate on the calculator, and what do I conclude? Okay, and then just make sure when you look in the back of the textbook, 7C, number 6, does it say what I think I should have written down? Okay, do try and do it for a few of them. I'm sorry for having run on a little bit with this one. but hopefully it's the last time now, as it is the last video. Okay, cool. I'll leave with that, and that's it for hypothesis testing.